In question number 6, a ball falls vertically onto a floor with momentum p vector and then bounces repeatedly. The coefficient of restitution is half. The total impulse imparted by gravitational force to the ball till it comes to rest is. So let this is the horizontal floor and the ball is released from the rest from this position. So due to the action of the gravitational force, it gains some momentum, and at the moment it is just about to collide with the floor, let it gain some momentum p, which is given in the question. Now after the collision, it bounces with a momentum minus e into p vector if I consider this as my positive sense. So it goes up and then goes down, and it about to collide the floor again with the momentum e into p vector. So if I write the total impulse imparted by the gravitational force to the ball, then it can be written as total impulse due to gravitational force is equal to the momentum gained by the ball from here to here, so that is p vector, plus change in momentum of the ball during this collision, second collision, is 2 into e into p vector, plus on the repeated cycle it is 2 into e square into p vector plus 2 into e cube p vector, and so on, and the final momentum becomes 0. So if I add all this, then it can be written as p vector plus 2e into p vector, then it can be written as 1 plus e square plus e cube plus so on, and the value of e is given in the question, that is half. Now if I substitute the value of e, then it comes out to be p vector plus 2 times half into p vector, and the summation of this gp can be written as 1 divided by 1 minus r. So the value of r is half, so 1 minus half is half. So it comes out to be p plus 2p, so that is 3p vector. So option 2 is the correct answer. Let's move to question number 7. In question number 7, two blocks A and B of mass m and 3m are connected by a massless spring of force constant k. The spring is stretched by an amount x and released. What is the velocity of block A when the spring comes to natural length? Let the velocity of block A at that moment is v, or the momentum of the block A at that moment is p. Then from the principle of conservation of linear momentum, we can say that the momentum of ball at the natural position is also p, so that the net momentum becomes 0. So we can also apply the principle of conservation of mechanical energy in this problem, as the work done by the non-conservative force is 0. So the initial energy stored in the spring is half kx square, and that must be equal to the kinetic energy of the block when the spring attained natural length. So the kinetic energy of the block A can be written as p square by 2m, and the kinetic energy of block B can be written as p square by 2 into m, and the mass is 3m. So if I solve this equation, the value of p comes out to be x by 2 into under root of 3m into k, and this p is equal to m into v. So the velocity of the block when the spring attains natural length is given by v, that is equal to x by 2 into under root of 3k by m. So option 3 is the correct answer. Let's move to question number 8. In question number 8, a uniform solid cylinder of mass m and radius r is placed on a plank of mass 2m as shown in figure. Plank is being pulled with a force of 10 Newton. If it is given that friction between plank and cylinder is sufficient to prevent sliding of cylinder, then tension in string will be. So if I draw the free body diagram on the plank and the cylinder, then suppose this is a cylinder, this is a plank. The force F of 10 Newton is acting on the cylinder in this direction. So due to the action of this force, this point has a tendency to move forward. So in order to oppose its motion, the friction will act in this direction, and the friction on the cylinder will act in this direction. The tension T will act on the cylinder in this direction, and the tension T on the plank will act in this direction. Let, due to action of this force, this point has a tendency to move in this direction with an acceleration a. Since the cylinder and the plank is connected by a string, so the acceleration of the center of mass is also a in this direction, and let the angular acceleration of the cylinder is alpha, then by applying the constraint of rolling motion, the acceleration of this point is alpha r minus a, that must be equal to a for perfect rolling. So the value of alpha comes out to be 2a by r. So if I write the equation of dynamics on the cylinder, we can write T minus F is equal to mass m into acceleration. On the plank, I can write F minus T minus F is equal to mass 2m into acceleration. And if I write the equation of torque on the cylinder, then I am applying torque is equal to I into alpha about center of mass. Since the center of mass is accelerating with some acceleration, so we have to apply a pseudo force at the center of mass, but the torque of that pseudo force about center of mass becomes 0. So the torque about the center of mass can be written as F into R is equal to I. Since it is a solid cylinder, so I can be written as mr square by 2, and the value of alpha can be written as 2a by r. So on solving this, the value of F comes out to be m into a. So this is small m. So if the value of F comes out to be ma, the value of T comes out to be 2ma from this equation, and the value of F comes out to be 5m into a. So we have to find out what is the tension in this string. So the tension in this string is given by 2ma, or that can be written in this way, 2 into ma. The value of ma is F by 5. Now the value of F is 10. So 10 by 5 is 2. So it comes out to be 4 Newton. So option 2 is the correct answer. Let's move to question number 9. In question number 9, a uniform rod PQ of length L is rotating with an angular velocity omega, while its center moves with a linear velocity v0 is equal to omega L by 2 as shown. If the end Q of the rod is suddenly fixed, the angular velocity of the rod will be. So we can apply the principle of conservation of linear momentum about point Q in this problem. So in ground frame, I can write, let the final angular velocity is omega dash, then by applying principle of conservation of angular momentum, m L square by 3 into omega dash is equal to m into v0 into L by 2 minus ml square by 12 into omega. And we know that v0 is equal to omega L by 2. So if I substitute this here and find out in terms of v0, then omega dash comes out to be v0 by L. So option 2 is the correct answer. Let's move to question number 10. In question number 10, in a gravitational field, G vector is equal to 8 I cap plus 6 J cap Newton per kilogram. Work done by gravitational force in moving a particle of mass 1 kilogram from 0, 0 to 3 meter, minus 4 meter will be. So if I find out the displacement of the particle S vector, then it comes out to be 3 minus 0 I cap, that is 3 I cap, plus minus 4 minus 0 J cap, that is minus 4 J cap. And if I see the gravitational field vector, that is 8 I cap plus 6 J cap. So if I take the dot product of gravitational field vector with the displacement vector, then it comes out to be 0. It means the displacement of a particle is perpendicular to the gravitational field. So the work done by the gravitational force as the particle moves from 0, 0 to 3, minus 4 will be 0 joule. So option 3 is correct. Let's move to question number 11.